Hello. So in this session I'll continue with 4 vectors and look at an example of how to apply this in a relativistic dynamics calculation. I'll start with defining some notations and deriving a few more 4 vectors to understand their properties. We have already looked in the last session on this 4 vector, which is made up of ct, x, y, and z. And I've defined a 4 vector as a vector that transforms according to the Lorentz transformation. Right, so let's represent this 4 vector by a letter, say x. It can be a capital or small letter, doesn't really matter. Okay, now one way to make some more 4 vectors is simply to differentiate this with respect to time. If I differentiate x with respect to time, you expect to get the velocity. If I write it out, I will differentiate each coordinate term by term. Now notice that I've, for time, used the symbol tau. Now, the reason is that tau here refers to the proper time. The proper time is the time in the rest frame of the body, the moving body. So in other words, it's the time from the point of view of the body, the moving body itself. Either if the body is an actual person or if there's an observer moving with the body. So we call that in the rest frame of the body. Now there's a reason why we would choose to differentiate with respect to the proper time, because the proper time does not depend on the other frames of reference. For example, for this particular 4 vector with coordinates x, y, z, t, these are the coordinates when measured from a particular frame of reference or by a particular observer moving at a certain velocity. And this would change if I change to another frame of reference, another observer moving at a different velocity. So the time will change as well in different frames of reference. But the proper time, meaning that if you're always looking at, if this is always the time, if you're always talking about the time of in the rest frame of the moving body itself, then that means we're always referring to that one same frame. So if we talk about proper time, therefore, it is always the time of in the rest frame of the moving body, and therefore it does not depend on any other frame. Okay, so we would want to use a proper time simply because if instead we use t, which is the time in a particular frame of reference, then it becomes different in another frame. And when I start having to differentiate it and transform it, it just gets a lot more complicated. So if I differentiate this with respect to the proper time, this is what I would get. And I would have a dt, the time in this frame divided by d tau, the time in a rest frame of the body, which is a different frame. So that looks a bit tricky to deal with, but if you think about it, the rest frame of the body simply means that from the point of view of the observer in this frame, he would see the body as moving. So that means that the time of the body itself, the time, say, of a clock moving with the body, would slow down. There will be time dilation. So that means the ratio of t dt to d tau, that means a time change in this frame to a time change in the moving object's frame is simply the Lorentz factor. So that's just the Lorentz factor. Right, let me write this down separately. So the time in the observer's frame divided the time in the body's frame should be the Lorentz factor because of time dilation. And this allows us to express this in terms of the more familiar velocity. So let's see, dx by d tau. Now the more familiar velocity would be just dx by dt, meaning that we differentiate x by the time in the same frame as the observer. So that's velocity as the observer sees it. Now to express it in this form, I would express this in this way, dt by d tau. So that's what dx by dt would look like in relation to dx by d tau. Okay. Now the dx by dt is just the vx, the familiar velocity component in the x direction. dt by d tau we already know, that's the Lorentz factor. So now we know how to write this. C times dt by d tau is gamma. Dx by d tau is gamma times Vx. Dy by d tau likewise is gamma times Vy, then gamma times Vz. Now we have what we would call the fall velocity in terms of more familiar symbols. Okay. Now just to introduce another way of writing this to make it look simpler, let's look at the Vx, Vy, and Vz. Now Vx, Vy, Vz, these are the components of the familiar velocity vector in 3 dimensions. So we would, we would call the V there the fall velocity. Alright, I would call this, by extending the terms, a 3 velocity. So if you hear the term 3 velocity, it just means our familiar velocity in 3D. And we would often represent it by a vector. I'm used to putting a squiggle underneath for the vector. But the other way to do it would be to have an arrow on top, which might be more obvious. So I'll use this notation for a vector. So that's a 3 velocity. Now in terms of this more familiar notation, I could write this as C gamma for the time component, or time-like component, and then I have this V, which is gamma multiplied by each of this. So I could write this as gamma times V, the vector, the 3 vector V. So that makes things simpler, rather than having to write out all 3 components. So that's the fall velocity. Okay, let's moving on. Right. Now we should also take a minute to think about why this expression is a 4 vector. Now it doesn't mean that it's a 4 vector simply because I've differentiated it from a 4 vector. Now 4 vector is a vector that must transform according to the Lorentz transformation, and the only thing we know so far that transforms according to the Lorentz transformation is the spatial coordinates, space and time coordinates. Now when we differentiate this, then we have in effect divided a small change, say in the spatial component, in the space coordinate x, by a small change in the proper time. Now dividing by a small change of a proper time is like multiplying by a constant factor when we're talking about Lorentz transformation, because the proper time does not change when you do a Lorentz transformation, since it always refers to the body's rest frame. So the d tau there is like a constant factor for the dx. Now the dx there is like taking the difference between two x values in this frame of reference. So if we transform the difference between two x value, right, it should transform according to the Lorentz transformation, because the difference is just a linear thing. So therefore, for example, dx should transform according to the Lorentz transformation, likewise for dy and dz and c dt. So this whole set of things in the numerator would transform the Lorentz way. Now the d tau at the bottom are just constant factors, so it's just a multiplying factor, and together therefore it will just follow the Lorentz transformation, and that's the reason why v is a 4 vector. So therefore, with this experience, we know that as long as we are just differentiating with respect to the proper time, we will always get something that transforms according to Lorentz. So the next thing that we could do is to differentiate the v. Then we'll get a 4 acceleration. But instead of doing that, I'll do something different. I would think about the momentum. So let's think about the momentum. What if I multiply the v by a mass? By multiplying the v by the rest mass. Or I could try multiplying by the relativistic mass. But let's start with the rest mass and see. So if I multiply this by the rest mass is also a constant. It doesn't change with Lorentz transformation, because like proper time, it always refers to the mass in the rest frame of the body itself. So it's the same thing wherever we are, in whichever frame it is. Now if we multiply this by m naughts, we would be multiplying each of the terms there by m naughts. So this is c gamma m naught, gamma m naught v vector. Okay, so that's that. So we would expect that if I'm just multiplying this 4 vector, 4 velocity by a constant m naught, constant as in the same for different frames of reference, then this product should also be a 4 vector. And this is what it looks like. So if I look at this, I can think of the gamma m naught as m, as a relativistic mass. Okay, and I can think of the m naught times v, the rest mass times the velocity, as our familiar momentum in 3D. So that would be our 3 momentum. Okay. So this would be a 4 vector. And let me represent this by the letter P. So again, it can be capital or small p, but the difference is that we would just write a normal letter. We would not make it a bold font, or we will not put an arrow above it. Alright, we will make the letter either a bold font or a letter above it when we are talking about the normal 3-dimensional vectors. Right, that's the 4 momentum P. Now next, let's have a look at the 4 force. Now we would get the 4 force by differentiating the 4 momentum. Again, we have to differentiate with respect to the proper time. Right, tau, which doesn't change with for different frames. Okay, and if I differentiate P, I will differentiate that term by term. This is what I'll get. Get C and dm by d tau and gamma dp vector by d tau. Okay, and that part there, this part here with the dp Right, let me make a correction here. Let's backtrack a bit to the 4 momentum. Now, this part here, as I've written it, I have I've called this m0 v the 3 momentum. Okay, that would be how we use it in Newtonian mechanics. But now that we are doing relativistic dynamics, the momentum should be the velocity times the relativistic mass. Alright, so the gamma should also be part of the P. So I should no longer have a gamma there. And that leads on to that as well. Right. So the gamma should not have been there. Okay, P means the whole lot. Velocity times relativistic mass. Okay, so with the 4 force, I now have this expression, and as with the 4 velocity, we would want to express this in terms of, express the tau here in terms of the time in this frame of reference, the t. So if you recall, dt over, we already have it here, dt over d tau was gamma. Alright, and from that we can express this as gamma c dm over dt, comma, and gamma dp over dt. Okay, and that's the 4 force. And this part of it, this part, without the gamma, just the dp over dt, where we recall P has included the Lorentz factor for mass increase. So this dp over dt corresponds to the 3 force, which is the familiar force in 3 dimensions. Alright, I might just call it F with an arrow on top. So that's the 3 force. Right, in case you can't see that better. Okay. Now, it might seem like a lot of hassle to take these familiar 3D quantities of velocity, momentum, and force and rewrite them into this abstract form with all these additional gammas and symbols and things. Well, the purpose of doing this is to make use of the facts when we need to do calculations, to make use of the fact that the inner product is invariant. Alright, to be precise, it means that, let's say if you start from a certain frame of reference, if we take any two of these factors, either a V or a P, or the P for two different objects. If we take the inner product of any two of these 4 vectors and find a certain answer, then if we transform these 4 vectors into another frame of reference and take the inner product there, you'll find that the answer should be the same. And this property is often helpful for us to do the calculation when we need to relate things between different frames of reference. It helps us to find answers to questions in special relativity. And we'll see that in the example afterwards. So for now, let me look at a simple example to demonstrate this property. Now this is the form momentum. What I'm going to do now is I'm going to make use of the invariant of the inner product to prove this expression. Now this is a familiar expression in special relativity that relates the total energy, right, including kinetic and rest energy, to the relativistic momentum and the rest mass. So how can we prove this? Well, we can start from mass increase, definition of momentum, and so on, and Lorentz factor. But that tends to get a bit messy in the algebra. But it can be quite simple if we use the invariance of the inner product. So let's see how we can do that. Now you have this body, say you have Imagine a body that is moving. With a certain momentum, say P in 3D, and it has a rest mass M naught. Alright? So let's see what we can do. The way to do it is to think of the flow vector. Now the flow vector in the rest frame, let's start with the rest frame, that's the easy one. In the rest frame, the mass M is just the rest mass. And in the rest frame, meaning the frame where they are moving with the body so that it is at rest, the momentum is 0. Okay, that's simple. Now in the moving frame, in the rest frame of the body, in the moving frame might not be a good word. Well, in the lap frame, rest frame and lap frame. Okay, these terms could be confusing. Now the frame, let me rephrase it this way. In the frame of the body, alright, the frame that moves with the body, so the body is at rest and therefore you have rest mass and 0 momentum. But in the frame of the laboratory, right, the lab frame, as we often say, from someone who is standing in the laboratory and looking at this body moving. So in the lab frame, the body moves and right, and the mass would be C times M. Okay, and the momentum would be some P. I'll just let that be the P vector. Okay. So now what I'm going to do next is to take the inner product between those two I'm going to take the inner product of each of this with itself. Let me call this, give it some name. So this is P, I'll call this P0, and I'll call this P1. Okay, call this P0 and call this P1. So I would take the inner product with itself. Now if you remember how to take inner products, we have in the last session, I've written this as a column vector multiplied by a row vector where the part that corresponds to time has a negative number. So if I do it for this, what I should get is 0 from there plus this multiplied by the negative of itself, so minus C squared M naught squared for the inner product. Alright, now just to make sure that we understand this correctly, the 0 here refers to the 0 of a momentum vector in 3D. So there are really 3 components of zeros here. So let me write this out. If I'm doing an inner product of this with itself would have the 3 zeros there for that part, and have the CM0 there. Alright, so we have this column vector here. And to take the inner product, we imagine writing out this in a row, CM0 and then 0, 0, 0. But we must put a minus sign in front. So and then we multiply this together like 2 matrices, and this is what you'll get. Alright, so likewise for that one, now instead of the rest mass, we have the relativistic mass, and we have this P vector there. So all these are P's now, Px, Py, Pz. So all the P's, X, Y, Z. 3 components. Right, so now if we multiply the 2, minus Cm and Cm, so minus Cm, C squared, M squared, plus the 3 components of the momentum and the 3 components of the momentum here. So we are essentially taking the dot product. So that would be the magnitude of the momentum squared. So in this case, P refers to the magnitude of the 3 momentum, of the normal momentum in 3D. Okay, so do not confuse the P there with the P here. You might want to think about the P there as a capital P, whereas the P there is a little p. So this P here is just refers to, just to make this very clear, the 3 momentum magnitude squared. Okay, that's what it is. So now I have 2 expressions, right? The inner product of the momentum with itself or in the body's frame, and the inner product of the form momentum with itself in the lab frame. And we know that they must be equal because inner product is invariant. So let's equate them. Right, okay, that's C squared M naught squared equals to minus C squared M squared plus P squared. Let's rearrange this. There's a minus sign there. Minus M squared C squared. Bring over to the left. P squared from there. And M naught squared C squared over to here. Now if you compare this with this, you see that we're getting there. Now the thing to do next is to relate the M squared C squared to the E. The relation is E equals to MC squared. Okay, so I would multiply both sides by C. By C squared. Right? So multiply this by C squared, multiply this lot by C squared. So when you do that, you get E squared here, you get P squared C squared, and you get M naught squared C4. So there, we've just proved the equation. So what you see here is one way to use the inner product. Now it seems a bit long-winded the way the time it has taken me to explain it, but I've mainly spent more time to explain how to actually evaluate this inner product and how to keep in mind the meaning of what it means when we say that the inner product is invariant. And once you get used to this calculation, all you need is to write this down, and you will be able to write down the inner product directly, so that these two steps will be pretty quick. And then it remains to equate the inner products between the two frames, and then to simplify the expression. Well, the next example I'll look at is a collider problem. So suppose that we have a proton and an antiproton. Now a proton, let the mass of the proton be m0, the rest mass of the proton. The antiproton will have the same rest mass. Okay. And the idea is that we want to collide the two protons, right? Accelerate them to very high energies, allow them to collide. So when a proton collides with an antiproton, they annihilate each other and turn into energy. Now the energy can take various forms, but part of the possible outcome, one of the possible outcomes is that it can produce new particles. Now in this case, we will look at the particular outcome where the collision between these two, this proton and antiproton, produces two W particles. So two W particles, I call them W1 and W2. Now the mass of a W particle, I call that capital M0, we'll take it to be 100 times the mass of a proton. Right? Now the question is to find how much energy energy we need to put in to the proton and antiproton, so that when they collide, there is enough energy to produce these two W particles. So the idea is that the mass of each proton is 100 times smaller than the mass of a W particle, but by putting in enough energy, the energy that we put in can then be converted into the mass of these new particles. And it would seem that, since E is equal to mc squared, and if I just look at this, that's 100 times the mass of this proton. All I need is to use an energy equal to m0 equal to the mass of a W particle times c squared. I just need to use mc squared, an amount of energy equal to mc squared of the W particle, apply this energy to the proton, to each proton, and allow the proton to collide with the antiproton. So it looks like that would be clearly an obvious way to do it. But in accelerator experiments, that's one way to do it, where we collide the two protons. But having two colliding beams in an accelerator could be tricky, more tricky for the design of an accelerator than if we have a stationary proton and a moving proton coming at it. So if one proton is at rest, we just put a material that contains protons in the middle of an accelerator, and if we simply accelerate a single beam at the stationary proton, say a single beam of antiproton coming at the proton, then the arrangement is a lot simpler, because clearly we just need to accelerate one beam. That should be a lot simpler than having to accelerate two beams, alright, which actually means that you need two accelerators coming together in effect. So, right, it is a lot simpler to just accelerate one beam, but the question is then, of course, if you just accelerate one beam, you will need more energy for that one beam. And the question is, how much more? Now, possibly in Newtonian mechanics, we might find that it might be just twice as much, or well, it will be more than twice as much, because one of the particles move, but it might not be that much more, or it might be, depending on the actual numbers. But what we want to do here is we want to calculate it in this relativistic dynamics, where energies can be a lot larger and the mass changes. We want to calculate how much more energy it will take if one proton is stationary and the antiproton coming at it is moving. How much energy would we then need in this situation? So we have two experiments that we want to check out. We have the experiment 1, in which we have a proton and an antiproton coming at each other. Alright, let's say that's antiproton and that's proton. And then we have an experiment 2, in which, say, we have a antiproton at rest, and we have just the proton, or maybe the proton at rest, and we have a beam of antiproton coming towards it. And we want to find out the amount of energy we would need for each case. And while we are looking at this, let's define some terms that we would use to refer to each of these cases. Now, in the first case, we are going to use two we are going to use protons and antiprotons coming towards each other with equal and opposite velocity. So this means that together, the center of mass of the two particles would be at rest, alright, because the momentums are equal and opposite. So we call this the center of mass frame, in short, the COM. So the center of mass frame means that in that frame the center of mass is at rest. We are in a frame that moves with the center of mass. Now in this case, the center of mass is not at rest. One proton is at rest, antiproton is moving. So the center of mass would be somewhere at the midpoint between the two, and it would move with this antiproton. Now in this frame, one of the particles is at rest. If you think of that that proton at rest as a target, we describe this as the fixed target experiment. So that's the fixed target experiment. That one is the center of mass experiment. And we want to find out how much energy is needed for each. So let's start with the center of mass frame. We have the proton, antiproton coming in at each other, and after they collide, they annihilate, produce lots of energy, and for some of the collisions, these energies would produce two W particles. Right. So let's write down the momentum. Now, I'll call that momentum P1. Okay, the form momentum. I'll call that form momentum of this P2. And I'll call this energy E. Call that energy E W. So let me write down the form momentum of the proton and antiproton before collision. P1, P2. Now if you recall the expression that I've written down for form momentum earlier on, it looked like this. MC, P. Alright. Now write this in a form that makes it easier to do the algebra in this case. I'll write MC as E over C. Alright, that's okay because E is equal to MC squared. So MC squared over C is the same as MC. So I'll use this expression instead, E over C for MC. So therefore, this is the form momentum for this is E over C comma P vector, the 3 momentum vector. Now for the P2, it's almost the same, except that because P2 has the opposite 3 momentum to P1, the sign is opposite. So these are the momenta of the proton, antiproton before collision. Alright, and we have already seen just now that the energy needed is quite obvious. We would need, you start off with this energy, and you need to produce a particle that has 100 times the mass. So the energy that you need must be more than m0 c squared. Alright, the energy needed for each proton or antiproton must be more than m0 c squared, which is 100 times of liter m0 c squared. So 100 times the rest energy of each proton. So this is a simpler experiment to calculate, but not a simpler experiment to set up. Okay, so let's that's that. Now let's move on to the fixed target frame. And the fixed target frame, I have a proton there, and I have a proton, anti-proton beam coming towards it. So when this anti-proton hits this proton, it produces, if there is enough energy, it produces the two W particles. So once again, let's write down the four momenta before collision. Before collision, this is the P. Right, let's say that's my P1 and that's my P2. Okay, so the P1 refers to this proton at rest. So the three momentum of P1 is 0. The E over C would be just m naught times C, the rest mass. Okay. Now this time, the energy I need would be different for this proton. Let me call it E primed. And I'll call the three momentum P primed. So the four momentum for the moving antiproton will be E prime over C P prime. Right. Okay, so what we are going to do next is that we need to find the amount of energy E prime that is needed to produce the W particles. Now we already know how much was needed in the center of mass frame. Alright, so to find out how much is needed in this frame, the way to do it is to relate E primed, the energy in this fixed target frame, to the energy in the center of mass frame. So we have two frames, we have quantities in the two different frames that we want to relate. And this is where the invariance of the inner product comes in useful. What we could do is we could take, say, the inner product of the two, of the P1 and P2 in the center of mass frame, which means those two that contains the E, and equate them to the corresponding inner products of the two momenta in the fixed target frame, which contains the E primed. So you see, then we can directly relate E primed to E. And then if we solve that, we will have an expression for E prime, and since we already know that E must be at least 100 m naught C squared, we would have an answer for E prime. Right? Now it turns out that it is actually, that if we do that, there might be a slight problem because the E prime there is an unknown that we want to find, but we also have the three momenta P and P prime, which are also unknowns, and that would be a problem. Now there is one way out. So this is something that just happens to work in this case, which is that we could consider P1 plus P2. We could consider adding those two for momenta. If you add two for momenta, the result is still a four momentum. Okay, because it's just a linear sum. Right, now why would we want to do that? Well, it's because, for a start, if we add these two, the P here and the minus P there cancels. So that simplifies it. That gets rid of one unknown. That. Now let's do it for this. So here we get m naught c plus e prime over c, comma 0 plus p, which is. So we are not so lucky here. We still have the unknown p prime there. Okay, the next step is to take the inner products. Now we have two inner products to take. One in the center of mass frame and one in the fixed target frame. Okay. Now if you remember, the first one was the center of mass frame. Right? The second one is the fixed target frame. That's refers to that picture there. Okay, so let's go with the center of mass frame. Now, instead of taking the inner product between, say, P1 and P2, since we see that the sum of P1 and P2 gets rid of the P, let's make use of that and take the inner product of this with either this or this. Now, which should we choose? Now, notice that if we look at this fixed target frame expressions, if I use this one for the P plus 1, and I have to choose either this one or that one to take an inner product with, notice that there's a 0 in that one, in P1. So that if I take an inner product between this and this, I'll get I'll be doing the dot product between P1, P prime and 0, and that would get rid of the P prime, which is the other unknown. So that's convenience. So therefore let me take the inner product between that and that. Okay, center of mass frame. So if you recall from the way I did the calculated the inner product in the example just now, when I multiply those two terms, that corresponds to the time position, I have 2e over c times e over c. These gains are minus sign. And then the other part would be this is actually a 0 vector, to take the inner product of this 3 vector with this 3 vector. Since this is 0, I'll just have 0 down here. Next, for the fixed target case. So in the fixed target case, it corresponds to another frame of reference. If you think about it, in the center of mass is where the two particles are coming together. Okay, in the fixed target case is where one of the particles is at rest. So that means this is the frame of reference where we are moving with that fixed particle. That's why the particle is fixed in that frame. Okay, so That's why this is another frame of reference, and if we take the inner product between this and this, I have m naught c plus e prime over c from there with this m naught c. And because this is in the time position, the minus sign there, and then I have to add the dot product between this 3 vector and this 3 vector. Since that's 0, that's 0. And it looks a lot simpler now. I have the e there, I have an e prime there, which I want to relate to the e, and there is no more p prime. So all I need now is to solve for e prime. Let's start simplifying things. So minus 2e squared. I multiply both sides by c. Okay. I can get rid of the minus sign, multiply both sides by minus 1. This would be m naught squared times c squared. I'm going to multiply both sides by c squared, so this becomes c4 plus, I have e prime there, I have m naught there, c and c cancel, but I gain an extra c squared there. Okay, so that's that. And now, finally, e prime is equal to it will be 2e squared if I divide both sides by m naught c squared, this will be m naught c squared minus m naught c squared. This. Right. I shan't do that. Okay. Right, let me rearrange this. I divide both sides by m naught c squared, and I write the e prime down here. Okay, divide this by m naught c squared. This is what I'll get. Divide that by m naught c squared. This is what I'll get. Now from the experiment 1, we know that E, which is the energy of a proton or antiproton, must be more than 100 m naught c squared. Right? The rest energy of a W particle. So that means that this must be more than, if I put in those values, 100 m naught c squared. Right, just plug those into there, over m naught c squared, which is 2,0,0,0 m naught c squared. 20,000 times the mass of the rest mass of a proton. So So therefore, E prime, which is the energy we would need in the fixed target frame, let's move that over to the other side, would be more than 20,000 minus 1 m naught c squared. Right, so nearly 20,000 times of the rest mass of a proton. Now if you compare this with the energy that is needed in the case of the center of mass frame. Now the center of mass frame, that's for one proton, so the center of mass frame requires at least twice of that, so twice of the 100 m naught c squared. Alright, 100 m naught c squared for each proton. So if you compare the two, you see that this is about 100 times more. That means that if you have a fixed target frame, you would need 100 times the energy for the incoming proton compared to if you're in the center of mass frame where both particles are coming together. Now because so much more energy is needed in the fixed target frame, that provides incentive for doing the experiment in the center of mass frame. In spite of the fact that you actually need, in effect, 2 accelerators to do it. You will still need that if you want to achieve enough energy to create the new particles. So that's the end of these 3 sessions on special relativity. Thank you.